So based off our information we've had previously, when we understand about how objects can move, they can move either in straight directions due to forces, or they can move due to rotation. When we talk about movement in general, movement is just the changing of its displacement or its rotation. And we know you can change displacement comes from if you have a velocity, you are changing your displacement. And you can change your velocity by changing your acceleration. So if an object is at rest, it has no velocity, right? Because it's starting at it's not moving. So then in order for that object to move, its velocity would have to change, and for that to happen, it means it must gain some form of acceleration. So reiterate it again. So for a body to remain at rest, its acceleration must be 0. We have our formula, F equals ma, so force equals mass times acceleration. Therefore, if we want our object to have a 0 acceleration, our force must be equal to 0. So we have an example over here, force equals mass times acceleration. If we rearrange it, we have acceleration equals force over mass. So therefore, if we want 8 equals 0, we have to get our force equal to 0, or our mass equals infinity, which we can't do, because most of the time our mass is constant. Okay, so what does this mean for us? It means if you have an object with multiple forces on it, so over here, this one over here, we have a 5 Newton to the right and a 1 Newton to the left. This object does not have a net 0 force. It has, if we add up those arrows, we're going to get a 5 newtons in this direction and 1 newton in that direction. So our resultant would be equal to that much. So it has a force. So therefore, this object will start accelerating in this direction. This object over here has a 5 Newton force, so it's going to go, this one's going to go forward by 5 and then back by 5. It's going to be back to the original point. So this object has no force, which means it is in it's not moving. This is what we call equilibrium. So let's get a rule, because I love rules. Rule: for an object to be in equilibrium, it must follow the following rules. The sum of all forces must equal to 0, and sum of all moments must equal to 0. So the first thing I've done is I've broken up the first rule over here. So instead of saying sum of all forces, I've said sum of all forces vertical has to equal 0, and sum of all forces horizontal equals 0. I split this up because the first questions we do with this are going to want you to split it up into vertical and horizontal components, so it's just easier to divide up into 3 rules, because it's usually the same process we're going to be working with later. But the third one over here is sum of all moments. We're lucky that our moments aren't split up in vertical and horizontal, they're just in one direction, so we can do that. So this is the graphically, when you write it in an exam or a question, this is actually the format that you're going to use. This over here, this symbol over here, this equals sign, this weird E. I like to think of it, this E stands for sum of all. Right? I know it looks like the E in equilibrium, but it means sum of all in math. So sum of all forces vertical. So sum of all forces vertical equals 0. Sum of all forces horizontal equals 0. And sum of all moments equals 0. So you obey these 3 rules, and then your system has to be in equilibrium, because there is no net force in vertical or horizontal. So it's not going to be moving due to a... So if we have no force, vertical or horizontal, then our it doesn't work. If we have no force vertical or horizontal, then we know over here this is going to be equal to 0, because it's going to have no acceleration. And if our moment equals 0, we're going to have no rotation. So that's how we know that. Cool. So now we know that what's going to cause it. How does this actually matter to us? We have a thing called a reaction force. So a reaction force is a missing or unknown force which must be put into a system to keep it into equilibrium. The simple example over here, we have a block. So a block has some gravity on it. So over here we have 50 newtons is going down. And what force can we put into the system to put it into equilibrium? Well, if you have a 50 newtons pulling down, if we put a 50 newtons going up, the total of the system is 0. So that's a very simple example, but that's what we're doing. We're putting an A force into the system to equalize it. We have our next, let's do our reaction force example. So We have a wheelbarrow. It has 50 kilograms of soil and produces its force 0.5 meters from the wheel, which it rotates around. If the handles are 1.5 meters away from the wheel, how much upwards force is required to keep the system in equilibrium? So the first thing we did here is we broke down the question. A wheelbarrow has 50 kilograms of soil and it produces a force of 0.5. This over here is like our first force, and I've already denoted it by the color. And it rotates around. If the handles are 1.5 meters, so I put this in green because it's our second force. We know its distance, we don't know its force value. Oh, there, hold on, we do. Let me get that green. How much upwards force? So we know, and we know the force is upwards, so we even have a direction. Is required to keep the system in equilibrium. So I highlighted equilibrium because it means we know that the system, if we add up all our forces, if we add up all our, if we abide by our 3 rules in this system, then the system should be in equilibrium. So let's go and solve this question. So the first thing I did over here is I did a diagram. So this over here is this first one over here is my pretty drawing, and then I broke it down into this case over here where I wanted to do it into a diagram showing this is what we call a free body diagram, where I don't have like the pretty stuff with the wheels. Now the first thing that's happening is I'm actually missing a thing in this question. Right, we have a wheelbarrow where we have our weight is pushing down by 50 kilos, and we have this force over here is going up by whatever this force value is. There's a missing force in this scenario. So when you have a wheelbarrow, if you've got to think about this, what is stopping your object from moving? So if you have a wheelbarrow and we have a weight and we're holding it up by one hand, what happens? What is that wheel connected to? What is stopping the wheelbarrow from accelerating towards the ground? Well, the wheel is actually producing some sort of force in this system. Right? We know that the wheelbarrow is producing some sort of force in this system because the wheelbarrow has to be holding up this weight. Right? Otherwise, our wheelbarrow it's going to get a scenario where it's just, so if we just have an upwards force over here and a downwards, if we just have an upwards force over here and a downwards force over here, the system's just going to want to start to rotate around this direction because we're going up here and down here. So it's going to twist around, and that's going to be no good. So we have to find we know that there's an extra force, and it makes sense. The wheel has to be pushing up onto the ground. So let's go and get this scenario, and let's pretty this up, and let's start doing this working out. So let me just delete some stuff. Okay. So over here we have this scenario. We have force over here. We have this force going up. So this is going to be our reaction force. Let's call it of the wheel. This over here is going to be our force. This is our reaction force of the handle, and this over here is going to be our 50 kilograms. And we have our distance. We know this distance over here is 0.5, and this distance over here is 1 meter. So the first thing we're going to notice is when we start doing our formulas for moments and such, we know that these over here are not at the right angles. So they're going to be slightly off. It doesn't give us the angle, but we're going to really take a shortcut. Since these are all dealing in the vertical, right? The angle doesn't matter because they're all dealing in the vertical, so they're all going to be at the same ratio. And if we imagine, I didn't actually say which angle the wheelbarrow is, so if we imagine if the wheelbarrow is lying down flat, that's not flat. If the wheelbarrow is lying down flat, we can still get the same scenario because it's just all about the ratio between these particular points here. So that doesn't matter. So, alright, first thing as we do this question, let's write out it's in equilibrium. So we know that sum of all forces vertical equals 0, sum of all forces horizontal equals 0, and sum of all moments equals 0. So let's start. Let's start with the easiest one. Let's start with, in this case, number 2 is the easiest one. Why? Because there is no horizontal forces anywhere here in this entire example. Right? All this is force up due to the wheel is pushing up. I'm going to pick a color. I'm going to pick all my orange will be on my horizontal stuff. So if we look at our horizontal force, we have a 0 and a 0 and a 0, so it's 0 plus 0 plus 0 equals 0. So yes, we already ticked our first condition. We do not have any horizontal force. Next one over here, we have to deal with, let's do sum of all forces, wrong color. Sum of all forces, vertical. Okay, so we have a vertical force for, so we know that it's going to equal 0. So let's start by bringing the 0 over here because we know sum of all forces vertical equals 0. So 0 equals, we have our plus, our resultant for the wheel. Right? We have a minus for whatever this fits. So this is 50 kilograms. We have to convert that into newtons. So that's 50 times 10. So that's kilograms, and that's gravity. That's our force going down. And then we're going to say our upwards force of the handle is RH. So, okay, the issue we have here is we have two unknowns, 1 and 2. So we can't actually solve this. But what we can do is we can put them as a ratio to each other. Let's say, so RW equals, RW is going to equal 500 minus RH. So later we can find this out. So, okay, let's try the scenario where we talk about our sum of all moments. So we have to pick a moment. We have to pick a moment, and we know our moments. We can add them all up. It's just we find the moment under each individual point. So let's say we're going to pick this point over here. Let's just pick the wheel. Can you see where I'm doing that? I'll highlight in green. Let's pick the moment around this point over here. So all right, let's just say sum of all moments. Oh, we're going to call this our point, let's call this our point W, because that's where our wheel is. So this is how we're going to write down our moments. We're going to say sum of all moments. Let's just say what point we're going around. We're going around point W. And let's just give us a direction. So we're just going to say that clockwise is positive, equals 0. All right, that makes sense. And so let's say, all right, our first point over here, where we have our force of RW. Let's just remember our moment equals force times perpendicular distance. So for our first moment over here, we have let's just say we have our moment RW plus our moment of our 50 kilograms plus our moment due to RH. So these are our 3 moments we're going to add up. When we do our moment of RW, we know that our force is equal to whatever our force of RW is, times, now what's our distance? If this force is going through this point over here, since it's going through the point, its distance is 0. Because if you imagine if that line, if it's on the point, it's going to be equal to 0. So, okay, so equals 0, that's fine. Plus, over here we have our value of 50. 500. Its distance is 0.5, and it is going in the clockwise direction, so it's positive. This one over here, we know its force is RH. Its distance is 1.5, and look at the direction, it's going in this way over here, so that's counterclockwise, so it's going to be a negative. So what we've done here is we've actually eliminated, let me just remove that counterclockwise. What we've actually done is we've eliminated RW because its perpendicular distance is 0. That's fine. This is exactly what we want, because now we can go to our RH equals, we're going to get a good value out of that. We're going to say RH equals, equals 500 times 0.5 over 1.5 equals 500 times 0.5 times 1.5. We plug in all these values, and then we are going to get a value of 166.6 recurring, so 1.6.7 newtons. Good. So we've found how much force is required. Now, if we want to go the next step, if the question asks to find and the force on the wheel, we can also do that because we can plug this equation into here, and then we can find that, which will mean should be 500 minus that, right? 500 minus 166.7. So our RW, so whatever the wheel is doing, is 3.3 newtons. So here we found, this is a very simple scenario where we found our reaction forces on, like this example is a wheelbarrow, by using the sum of all forces, vertical, horizontal, and moments.